Okay, ji, Bismillahirrahmanirrahim. Welcome to another lecture of modern control systems. Today we will be discussing two important topics, root locus and PID control. I am your presenter Muhammad Rafi Chokhtai. So let's start the lecture. The first topic that we will discuss today is root locus method. Root locus method. Root locus, what actually root locus is, you people already have some idea about the root locus, that how root locus is formed, what is root locus. For example, we already discussed that if you have some poles of the system over here and over here, let's suppose we have a system with two poles, and these poles are actually the roots of the characteristic equation. The roots of the characteristic equation defines the poles, and this characteristic equation is made up of zeta. So you can change this characteristic equation by changing zeta, or you can change the zeta by changing system parameter, just like in your mass spring system it was dependent upon k, b and m. So by changing spring constant, the frictional constant and the value of the mass, you can change the zeta, you can eventually change the characteristic equation, and eventually you can change the location of the poles. This you are doing intentionally. You are moving your poles to some location by changing k, b and m. But what happens if zeta changes automatically? For example, if either automatically or by some controller. For example, if you want that your system should be non-sensitive towards disturbances, and those disturbances have some tendency to change your parameters, internal parameters, such that your zeta is being changed. For example, in case of your mass spring system, for example, with time the frictional constant may change, with time the spring constant may change, so your system zeta will be changed, and eventually characteristic equation will be changed, and eventually the location of the poles will be changed. So new system has maybe poles at this location, and when the system gets old, maybe the poles of the location is somewhat changed to this location, maybe. So one way is to change the route or pole location with the help of by changing the system parameters. Another, it may change automatically due to degradation of the system. Another reason for the change in route or pole location is the controller that you are using. For example, you are using a controller with gain k, that we discussed in our this example. In our last example of this one, we have a controller with the gain k. So we obviously whenever this gain, the value of this gain k will change, the zeta will change, the characteristic equation will change, the location of poles will be changed. So we have concluded that location of poles can be changed. But obviously, you should change the location of poles, keeping in view that the poles do not cross this j omega axis, and they do not come into the right half plane. And from this, you define the ranges of the k, b, or m, or this controller k, just as we defined the ranges of k and a in our previous lecture. So you have to take care of this element, that you're either, if you are changing the location of poles by yourself, you shouldn't change the k or any variable parameter up to an extent that the pole moves to the right half plane. So once we have decided that poles can be moved uh, in a controlled movement by changing the k, b or m or any system parameter, once we have established this, second thing that we need to know is the path that pole follows when you change either K, B or M or automatically or this controller. So if you have all of these three methods to change the location of the poles, there some be must pattern which a route or a pole follows for some specific characteristic equation, because obviously the nature, the composition of the characteristic equation is same. You are only changing the uh, parameters of the characteristic equation or the variables, or only in some cases you are only changing the gain k. Rest of the systems remain same. So we need to know that what would be the path that route follows when you change this gain factor k. For example, uh, if you have a pole over here and you want to change your gain k and see what happens. Let's say you change some value, it comes over here, then it comes over here, then it comes over, and then it moves to the right half plane. So this is the path that route has followed. This path is called route locus. This path is called route locus. If if I am able to somehow draw the route locus, and I have a route over here, and someone asked me to draw the root locus of this system, and let's suppose its root locus is this line all the way up to minus infinity, then for this system, whatever the value of k you assume, the system will always remain stable, because you will change zeta, you will change the gain, you will change any system parameter. This system will never gets unstable. This will be a highly stable system, because whatever you do, the pole will either lie over here or 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 up to minus infinity. Whatever the value of k or whatever the value of zeta you are taking, the roots will always lie on this path, which we have called a root locus. So this is also helpful in cases where you need to design a system, or let's suppose another example. Let's suppose you have a pole over here, and it moves to the j omega axis via this path. This is a root locus, and you want to make this system a stable system. Then what should you do? What should you do? You just add a 0 over here. Always remember, a root locus starts at a pole and ends at either 0 or infinity. Root locus always starts at a pole, obviously, because this is a path that root has to take while you change the system parameters or the zeta. So the root locus always starts from the pole and ends at 0. If there is no 0 available, it will go to infinity. If there is in search of some 0, obviously. So if there is no 0 available, it will go to infinity. So if your root locus is going to infinity, you can stop it from going to infinity by inserting a 0 over here, and your system will automatically will become a stable system. Whatever the value of k you will assume, whatever the value of zeta you will assume, the roots will always lie within this portion whenever there is a 0 over here. So in this case, the pole path was from this point to minus infinity. So we assume that whatever the value of zeta or anything you have out of these three methods, your system will never become unstable. And in the second example, your system was becoming unstable when root or pole crosses this j omega axis while going to this path to the infinity. However, after inserting a 0, it terminated at 0, and the root locus will only be this portion. And obviously, if root locus is only this portion, then root locus means the path of the path that root takes. So if the path starts from here and ends at here, then obviously the root will never go to the right hand side, of the plane, and this system will always remain a stable system. So this is the concept that we need to know for before we start how to draw a root locus. So from this you can imagine the importance of a root locus, that if you know the path that root takes while you change zeta or you change any other parameters, you can conclude that whether this system will become unstable or not, or whether this system uh, or whether this system has some zero to which its root locus terminate, or whether it is need to add some zero to make it stable or not. So the information obviously are very useful. So in order to draw, how to draw the root locus is our next question. How to draw a root locus? For that I will take an example from your Dorf book. This is page number 461, example 7.4. So we will see how he has drawn the root locus for this equation, and then obviously uh, uh, actually this example has everything, every steps covered, so that is why I am interested to explain this example. So once if you are able to understand this example, you can draw any root locus given to you. So you are given with a fourth order system. We desire to plot the root locus for a characteristic equation of a system as k varies from k to k greater than 0. So it is given that you have a system in which your k is a variable term and k is varying from 0 to infinity, and obviously as k will vary, your system or your root locus will change. You may have noticed that what is this form? What is this form? This form is actually, if I tell you it is, okay, let me, okay, you have g of s over 1 plus g of s for your unity feedback systems, and g of s into h of s for your non-unity feedback systems. So this term obviously is your characteristic equation. So he has actually written this term 1 plus g of s into h of s, or 1 plus g of s over here. Why? Because to start drawing the root locus, it is convenient to have your characteristic equation in the form of 1 plus k into something, so that you keep k separate, and you can have the effect of k on your system. So this is actually the form of 1 plus k into something, which something is 1 over this term, this term. So he has actually written the characteristic equation in this form. So this is in fact a characteristic equation, 1 plus g of s either into h of s, or simply 1 plus g of s. So first of all, obviously, we determine. Let's go to the step two. Firstly, he has written your problems. Actually, the problem statement is already given in this form. But if it is not given in this form, uh, you would be given with enough info. You would be provided with enough information to make it in to or either to transform it into this form. In this question, it is already in this form, so no need to worry. So first of all, determining the poles. One pole we have at origin, s is equal to 0. Another pole I have at s is equal to minus 4. Another pole I have s is equal to minus 4, minus 4j, and minus 4 plus 4j. Okay, as this book has already drawn the root locus, let's draw our root locus for this specific problem over here as well, just for be able to do it step by step, because uh, in the book everything is drawn simultaneously. For example, where is the root locus? This is the root locus. So it seems quite complex to you at the moment, but once you will complete all the step, it will be very uh, easy to understand. So I will start with a scratch. I have just S plane. So first of all, draw the poles. Where are the poles? One is at origin, one is at S is equal to -4. So one pole at origin, 1, 2, 3, 4. One pole at S is equal to -4. Okay. Another pole -4 minus 4j and -4 plus 4j. 1, 2, 3, 4. 1, 2, 3, 4. So another pole over here and another pole over here, because it is plus 4j and it is minus 4j. So I have drawn the four poles for this fourth order system. So we have just started with scratch to draw a root locus. First of all, see, as there are 1, 2, 3, 4 poles. So when you will change k, these all four poles will change their location. It means you would have four, you can say four loci. You have four parts of the root locus. This root has his own path. This root will have its own path. This root will have its own path, and this root will have its own path. So the overall root locus will consist of all of these four paths. So the poles are located on the S plane. We already know, because the number of poles n is equal to 4. We have four separate loci. He has already told us. Okay, the root loci is symmetrical with respect to the real axis. Yes, 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 yes. Means this is the real axis. If you have drawn the root locus in the upper half, you can symmetrically draw the portion root locus in the lower half. For example, if you have drawn the path of this pole, you have drawn the path that this pole will follow, you can automatically draw the path of this pole with the help of symmetry. So it will this every root locus has symmetry around this real axis. The whatever the root locus is in the upper portion, same will be in the lower portion. So we will make use of this property in this question as well. So the root loci are symmetrical with respect to the real axis. What is the second step? Second step is, so let me write steps as well. So step 1 is to plot poles of the system. What is the second step? Once you have drawn or plotted the poles of the system, segment of root loci exist on real axis between s is equal to 0 and s is equal to -4. Yes, it means that if you have 1, 2, let's forget it. Let me draw over here. If you have 1, 2, 3, 4 poles over here, then portion of the real axis from first pole to second, third pole to fourth will be the part of root locus. It means that your roots, there is a road over here, and your roots will come, any of these two roots will come on this road, and they can move across this road. So actually root locus is if you imagine this, root locus is actually drawing the motorways for your routes, or drawing the roads for your routes, which they will follow while you change your gain factor k. So the first point that we know, that there will be a road at this portion and this portion of the real axis. At the moment, we don't know that whether this pole will move over here or what would be the direction. We will find out shortly. But one thing, that if you have it always starts with odd number of pole. For example, from first pole to second, third pole to fourth. If you have a fifth pole, it will have portion of root locus from here up till infinity. So first to second, third to fourth, and then fifth to infinity. However, if there is a sixth pole over here, then instead of going to infinity, the portion will be from fifth to sixth pole. So for our question, from first to second, it means from here. Okay, let me draw root locus from some other, or rather with the same pen. So this portion of real axis is the part of your root locus, and roots will come to this portion. Roots can come to this portion of the real axis. So the segment on the of the so a segment on the root locus exists on the real axis between s is equal to 0 and s is equal to -4. We have discussed this. Now next is the angle of asymptotes. What is the angle of asymptotes? Angle of asymptotes are actually the paths uh, that the asymptotes are actually the paths which poles follow to reach infinity. For example, um if your pole if you have this pole and it do not have any there is no other zero in your system, and you have only single pole, then this pole will obviously move to infinity. But now you don't know which path it will follow to go to infinity. It can go to infinity via this path, via this path, via this path, via this path, any path it can take. So to find which path it will take while going to infinity, for example, if I already have this asymptote drawn, then obviously this pole will go to this asymptote, this path, and it will move to infinity along this path. If I know the angle of asymptotes and the center of asymptotes, if sorry, I to make you a good understanding, I would say, if I know this line, if I know where this line is, or in total layman term, I can say that I have to draw a motorway till infinity. So let's suppose I have drawn these two motorways that are going to infinity, and there is a pole over here and there is a pole over here. So this pole will follow this motorway to go to infinity, and this pole will follow this motorway to go to infinity. So this is a part of root locus, whereas these are the uh, these paths are not the part of root locus. These are just the asymptotes. However, the whenever the path follow this road, then this becomes a part of root locus. So asymptotes is just drawing these uh, facilitating routes with the path that they can follow while they are on their way to infinity. So for this, to find the paths, you have to find the center and angle of asymptotes. So once you know the center of asymptote and angle of asymptote, you can draw these lines. How? So the angle of asymptote is phi of a equal to 2k plus 1 divided by 4 into 180, where k is 0, 1, 2, 3, and 4 is the number of poles. So 2k plus 1 into 180, you can have k0, you will find one angle. You can have k1, you will find another angle, make k is equal to 2, you will have another angle, and k is equal to 3 and you will come up with another angle. So 45, 135, 225, 315, and then this again will repeat while you have other or subsequent values of k. So for k is equal to 4, it will again come to 45 degree, and then this cycle will repeat. So I have 45, 135, 225 and 350 degree of angle of asymptotes. So now the center of asymptote is found by, okay, they haven't given us the formula over here. Center of asymptote is actually sum of poles minus real part, sum of real part of poles minus sum of real part of zeros divided by poles, number of poles minus number of zeros. So this minus 4 is this minus 4 is this, this minus 4 is this, and third one minus 4 is this, and there is no another one because this is for this the real part is 0, and there is no 0 over here, so minus 0 is they haven't written minus 0, and number of poles 4 minus number of 0 0, so it is minus 3. So angle of asymptotes are 45, 135, 225, 315, and center of asymptotes minus 3. Let me draw over here with what pen? Let me use red pen. Okay. So my asymptotes are centered at minus 3 over here, and one is at 45 degree. It means this one. This is 45 degree, and another one is at 135, 225, and 315. 135, 225, which would be like this, this, and this. So I have drawn the asymptotes. Let us see the asymptotes in your book. So these are basically asymptotes. These are your asymptotes. So next step. We are done with the first step. We have drawn the we have located the poles on the j omega on the s plane, and then we came to the conclusion that this part of the real axis is the part of the root locus, and next step was to draw the asymptotes. For that we needed a center of asymptote and angle of asymptote. So once we have center and angles, we have drawn these lines with the help of that information. So after center of asymptotes and angle of asymptotes, let me clean this. Okay, now the next step is tell us when the root locus crosses the j omega axis. So let me write it over here. Plot the poles of the system. Next step was to identify portion of real axis which is part of root locus, and the next step was to draw asymptotes, and another step is to find point where root locus crosses the j omega axis. So next step is for the point we need that we would like to know the point where any of these poles crosses the j omega axis, if it will. I mean, we will come to the conclusion if there is a possibility that by changing k, these poles can move towards the right half plane, then our next step will give us the exact point where these poles will cross the j omega axis. Either they will cross j omega axis at this point, at this point, at this point, at this point, or any point. So to find that point from where this our poles will cross the j omega axis, we will obviously take help from the Routh. Obviously, you know that Routh can give us the boundary of your stability, because Routh tells you that if there is no sign change in your first column, your system is stable. But however, if there is a zero over here, your system is marginally stable. So we can make use of this property. We would make any entry equal to zero, and then we will find the value of s. That when this entry is zero, what is the value of s? So that value of s would be the point where the system is marginally stable, and obviously at that point your poles will be crossing the j omega axis. So let me repeat, or you can listen to this again. You should listen to this again. Okay. So I have this characteristic equation with me, S4 plus this is equal to 0. And from this characteristic equation, I have drawn a Routh array, which is 1, 12, 64, 128k, 1, 12, 64, 128k. And this term B1 should be 28 into 1 minus 12 into 164 minus 128 divided by 12. This is B1, and you can write 53.3 in place of B1, and this is K, and in place of C1, which is 53.33 into this one. This is the expression for C1, this is the expression for B1, and this is K. So from here, when we make C1 is equal to 0, when we make C1 is equal to 0, it means that we have a 0 at this point. If we have a 0 at this point, there is already 0 over here. We already have 0 over here, and there is a 0 at this point. It means that your system becomes marginally stable. There is a 0 row over here. So if your system is marginally stable, it means that you have poles on the j omega axis. So at what value of k you have poles on j omega axis, make it equal to 0, eliminate k, you will find k is equal to 568.89. So at k is equal to 568.k89, uh, you have your pole on the j omega axis. So the auxiliary equation for that, it is a zero row, then auxiliary equation will be over here, which is bs square plus 568.89, which is the value of k. So from here you can calculate s by putting this value of k. You know, at this value of k your system is marginally stable, so put that value of k over here and you will find the value of s. So at this point 3.266j and s is equal to minus 3, sorry, s is equal to minus 3.266j and s is equal to plus 3.266j, your system is, or your poles are crossing the j omega axis. So let me draw these point 3.266, 3.266. So 1, 2, 3, 3.2, which will be over here. 1, 2, 3, this will be over here. So these are the points I have identified from where my poles are crossing the j omega axis when you would have k greater than what, 568.89. When your k is equal to 568.89, your poles are exactly at j omega axis and exactly at this location, 3.266j and minus 3.266j. So in this way, we have found the points where it crosses the geometry axis. So what is the next step? Next step is to find breakaway point. So what are the breakaway points? What are the breakaway points? Breakaway points actually are the points. Okay, this is the pole and this is the pole. We know that this portion is the part of root locus. It means that this pole will move over here and this pole will move over here. However, there will be the point where these two poles will collide. And when these two poles will collide, one will move upward and one will move downward. So any of them can move upward and any of them can move downward. One of the pole which is moving upward, whatever behavior it will show, same behavior will be shown by the lower one because they are symmetric, because the root locus is symmetric around real axis. So it doesn't matter if you say this pole is going up or this pole is going up, it doesn't make any difference. So there will be a point where they will collide and one will go up and one will go down. So what will be that point is called a breakaway point. So we need to find that breakaway point. Now what is the procedure to find that breakaway point? If you eliminate k from this equation, k would be minus s4 into somewhere minus s4 into minus s4 minus 12s cube minus 64x square, which is eventually this. Now you know that the range of s over here is 0, 2, 1, 2, 3, 4. The point from where they will break away would be between 0 and 4. Obviously, common sense, I would say. Because either they will break away from here, from here, from here, from here. The breakaway point would be the range of breakaway point will be from s is equal to 0 to s is equal to minus 4. So any value of s from 0 to minus 4, they will any of these both of these two poles will break away at any value between 0 to minus 4. What would be that value? What would be that value? That would be the value where the value of k is maximum. For example, you have expression of k over here. Put the value of s from 0 to minus 4, and the point where you get the maximum value of k is the breakaway point. Simple. For example, look at this table 7.3. You are putting the value minus 4, your p of s or this k value is equal to 0. You are putting s is equal to 0, this is 0. So you are moving towards right, minus 3, the value is increasing. And from here you are moving toward left, minus 1, your value is increasing. So it is kind of this trend. So this at this point, this will be the point where the poles will break away. So at minus 3 your p of s is 51, at minus 2.5 it is 68, and minus 2 it is 80, minus 1.577 it is 83, and minus 1 it is 75. So it is now decreasing. If you see, it is increasing after 1.5 it is decreasing. So over from here it is increasing, and from after minus 1.577 the value starts decreasing. So this is the point. S is equal to minus 1.577 is the point where your poles will break away. So 1.577, this point. So at this point your poles will break away. So I can draw the root locus for these two poles. at the moment, not for these two poles. I can draw because for these two I need one another information, but for these two poles I already have all the required information to draw the pole, to draw the root locus for these two. So so this pole is moving toward right and this pole is moving towards left, and at this point one pole is up and one pole is down. And now I know they are crossing the j omega axis over here, so they are going towards this, towards this. At this point they will cross the j omega axis and then they will get aligned with this asymptote, and then they will move to, this pole will move to infinity via this path. Similarly, same will happen for this pole. It will cross the j omega axis at this point, and then it will coincide itself with this asymptote and it will go to infinity via this till infinity. Similarly up to infinity. So we have made use of the breakaway point. We have made use of the points where they have crossed the j omega axis, and then we have eventually made use of the asymptotes to draw this path which these two poles will follow when you will change your k. So I hope you people have understood the how I have drawn this root locus for these two poles. Let's see in the picture. So this is the root locus for one pole and this is the root locus for the second pole. So what about these two poles? First thing we know for sure that these two poles are going towards infinity via their nearest root or their nearest asymptote. So this pole will go to infinity via this asymptote, and this pole, sorry for my drawing, they are not symmetric. However, consider these symmetric and equal distance from here to here and from here to here. So mm, let me make it symmetric. Okay, so we know this for sure that this pole will follow this path and will go to infinity, and this pole will follow this path and will follow infinity. But we don't know that whether this pole will go to this path either by this or by this pattern or by this pattern or by this pattern. We have no idea about this. So we know that there is a motorway near to it, but uh, we don't know the orientation of the interchange to reach that motorway. Motorway is, or the ring road is in sight, which is going to the infinity, but we don't know about the interchange or the path that I follow to reach that motorway. So that path or uh, that interchange will be given to you by our next point, which is angle of departure. So next step is to find the angle of departure. So angle of departure of pole P1 or P2 can be estimated by actually it is the angle that all the uh, poles subtend to that pole. Sum of all those angles is equal to 180 degree. 180 plus k into 360. Actually, let me try to explain it in this manner that theta 1 is the angle. For example, if you want to find the angle of departure of this, then let's say angle of departure is theta 1. Then this angle of departure theta 1 plus the angle that this pole subtends to this, angle that this pole subtends to this, and angle that this pole subtends to this. For example, this is theta 1, which is the angle of departure. So and plus theta 2, which is the angle that this pole subtends with this pole, plus theta 3 is the angle that this pole subtends with this with respect to the real axis, and theta 4 is the angle that this pole subtends with this. So this pole subtends 90-degree angle with this pole with respect to real axis. Same is the case with this. So theta 3 and theta 4. These are 90 degree, 90 degree. Theta 1 is unknown, which you need to find. Now, what is theta 2? So, same is over here. He has only changed the name. So, theta 2 in our case is 135 degree. So, by inspection, you can say this is 135 degree. So, you know theta 1, you know theta 3. So, sorry, theta 1 you want to know. You know theta 3 90 degree, theta 4 is 90 degree. What is theta 2? 135 degree. This angle is 135 degree. This angle is 135 degree. This angle is 90 degree. This angle is 90 degree. So sum of all these all these angles you can say is equal to 180 plus k into plus k into 360 degree. So from here you can find theta 1 which is equal to minus 135 degree. So theta 1 is minus 135 degree, theta 1 is minus 135 degree, this is theta 1 which is minus 135 degree. So minus 135 means it will go to from here. Okay, from here it will move to, it will make minus 135 angle degree, and then it will reach the asymptote and will continue its journey. Let me draw with that blue ink which we were using for root locus. So by symmetry we know that it would be like plus 135 degree. So these two poles will go to infinity via this path. These two poles will go to infinity via this path, and whenever you will change the value of k, these 1, 2, 3, 4 poles will always follow the path in this blue ink. No one will go any other position in this complete S plane. They will always follow this path. Let us see from your book as well. So yes, minus 135, and this is the point where they are leaving. The angle of departure gives you the point when they are leaving, and from there you have to whenever they left their position and the point they reached the asymptotes, they will then follow the asymptotes till infinity. So our root locus procedure is complete. Let me recap. First of all, we plotted the poles of our system, then we identified the portion of the real axis which was the part of root locus. Then we were able to draw our asymptotes. Then we found the point where root locus crosses the J-mag axis, then the breakaway points, then the angle of departure, and here we are with our root locus for the system in this example. So the second article or the second topic that we are discussing today is PID controller. PID controller is actually a very important controller with respect to its application in the industry or with respect to its application in design examples. Uh, Yeah, when you will go to the industry, you will see that PID controllers are everywhere because loops are everywhere, feedbacks are everywhere. Uh, when I say this, I say that, for example, uh, if you are in an industry where, uh, let's take a scenario that there is a vessel which is being filled with a tap, and this tap has valve over it, and this vessel has a level sensor. So whenever the liquid is pouring, your logic or your program that you have written is this, that whenever this sensor sense that level of the fluid in the tank has reached this point or reached the set point, then close the valve. So this closing of the valve, obviously this is a feedback loop. Uh, you have the response or you have the sensor installed at this point. This sensor will give information to your controller, and this controller will then give command to this valve to either open or to close. Now the command will be given to the valve, and obviously the valve will follow some pattern. For example, if valve is closed and this is open location and this is closed location, then whenever this controller will give command to valve will not instantaneously open. The valve will follow some pattern. That pattern we already have discussed. So this pattern, I am repeatedly saying that this pattern is of critical importance because it gives you the response of your system. So whenever this valve will open or this valve will close, it will not open or close instantaneously. It will obviously follow some pattern. So this pattern is of critical importance. Whatever this pattern is will you can say will define the life of the valve. For example, if there are vibrations or if there is an error, life of the valves as well as the product quality which is being manufactured in this factory. Because if there is some steady state error, this is open, or you can say if this is close point and this is open point, your valve should close, but there is a leakage of steady due to this steady state error, your valve is slightly open. It is not completely closed, it is slightly open. Then obviously your product quality, your levels will be changed, your product quality will differ. So we need to stop this leakage. We need to install something, we need to install some controller, we need to install something which checks, which examines this steady state error and reduce it to zero so that there is no effect on the product quality. And further, we need to have some controller which reduces the vibrations, which will eventually or subsequently uh, increases the life of this valve. If there are vibrations in the valve, the life of the valve will be reduced. and if there is a steady state error, the product quality will be deteriorated. So we want to reduce vibrations, uh, we want to have zero steady state error. So if there are vibrations, and if your valve have this response of the valve has overshoots and ripples, and your plant have thousands of valves installed, then imagine of the investment that you would have to make when all of these valves will fail. Obviously, it will be a huge investment. So from investment point of view and from quality point of view, it is very important that this response of this valve is of critical importance in terms of quality as well as the life of quality of product as well as the life of the product. So this response of the valve is being controlled with the help of an external controller. This is, let's call this one as PLC so that we do not confuse it with PID controller. So PLC, which is executing the process without any controller, without any external controller. So actually I'm trying to say that this is a K and this is G of S. This is the G of S, where G of S is the process which says that sense this level and close the valve. And then you need to have a controller this which reduces these things, which increases the life, uh, which reduces the vibrations and reduces the steady state, and obviously any other factor which affects the product quality. So from this you can well imagine that PID controllers are everywhere in the industry, and the term that people use in the industry is to tune PID loop. PID loop should be tuned. If the PID loop is properly tuned, then obviously, uh, or it is subsequently called loop tuning. So loop tuning is of critical importance in your industry because it saves a lot of revenue in terms of increasing the life of your valves. Obviously, how it increases the life by reducing the vibrations, and it increases the product quality by making the steady state error is equal to zero. So that is why your controllers, or specifically your PID controller, is important. So if I draw now, what is PID? Let's start with scratch. P is okay. Let's start with scratch and just discuss what PID do. P is proportional term, I is integral term, I is integral term, and D is derivative term. And D is a derivative term. So let's briefly discuss what are the benefits of PID. For example, if you have a system over here, this is the final, or you can say a set point. There are two terms that I will use. One would be set point, which is actually the desired value, and next is the process variable, which is the actual or instantaneous value. Instantaneous value. So this is the set point and this is the instantaneous value. So at this point, the difference between instantaneous value and set point is greater. At this point it is less, at this point it is again greater, and at this point the difference between this set point and difference between this process value is this, which is called as uh, SP minus PV is equal to steady state error. So initially the error is greater and eventually error is reduced and then error is constant. So what this proportional term will do, this proportional term is simply a gain factor K, which is directly proportional to the error E. So this proportional term, uh, here the steady state, here the overall error between PV and SP are greater, so this value of Kf will be greater. And here it is 0, so this value will be 0. So this value of proportional controller would be proportional to the magnitude of the error. So eventually it will be an amplified kind of response when you have installed a proportional controller. It would be better if I draw it with another pen, but on the uh, same. For example, it will be like amplified version of the, obviously as it is a hand drawn drawing, so it is not that much accurate. You may browse any pictures over the Google for responses effect of a proportional controller on the response of a system, then you will have these types of diagram appearing in the Google. So you may have the accurate responses for some accurate values of K. For example, if K is equal to 2, then it will be amplified to this level. For K is equal to 3, it will be that. So the crux that I would like you people to understand is that the proportional controller, the gain of the proportional controller is directly proportional to the magnitude of the error signal. So if you see that the rise time of response should decrease in case of proportional controller. Similarly, if the rise time is decreased, then obviously overshoots will increase. So the rise time, your proportional controller has decreased your rise time, which is a good thing. However, it has deteriorated your overshoots. It has increased your overshoots, which is a bad thing. So obviously there is a trade-off. We use these PI and D controllers in combination so that effect of the bad impact of one controller is compensated by the good impact of another controller. We will see this later in this lecture. So at the moment we are focused on only uh, proportional controller or proportional term whose gain is directly proportional to the value or the magnitude of error. So we have seen that rise time of this controller, it decreases the rise time of your system. It increases the overshoots. Um for settling time, I think there will be a very small change for the settling time, and the steady state error will obviously decrease. So after proportional term, let's discuss integral term. What do what impact integral term have on our system? Um, Again, it's the gain or output of this controller is again dependent upon the value or the magnitude of the error signal. Uh, all of these three controllers are kind of driven by the magnitude of the error signal. But all of these three treat that error signal differently. For example, proportional controller just makes its gain exactly proportional to the value of the error signal. However, the integral controller doesn't do things like this. Integral controller, what is integration, by the way? What is integration? If you have a straight line, let's suppose if you have a straight line, the integration has the property to convert the straight line into a ramp or into a slope. However, the derivative makes slope to a constant. So integration makes a constant to slope. What does this mean? Why I am discussing this? Integration has impact on the steady state error when there is when there is some steady state error. Let's suppose this. Then this due to this steady state error, there is some value. Your integral controller will convert this value to a ramp. So let me try to draw it more neatly. Let's suppose this is the set point and this is your variable. So there is a steady state error. It will convert it into the slope. It will go over here. And then after a small shoot up, there is still a steady state error. It will convert it into a negative slope. Then there is still a steady state error. It will convert it into this. Eventually, it will get aligned with your set point. So integral controller has the capability to make steady state error equal to 0. So this integral controller can altogether eliminate the steady state error. However, as you can see, the settling time gets increased. Settling time increases, but steady state error is equal to 0. This is a very uh, beautiful property of integral controller and one of the main reasons it is being used in the industry to reduce the steady state, to eliminate the steady state error. So just imagine the example of this valve again. So initially you would have been thinking that it would be ideal if this valve is completely open or completely closed. Yes, we can make it possible by installing an integral controller behind our G of S. This is G of S, which is actual process of closing this valve. If we install a integral controller with this G of S, our system would have capability to make steady state error or to close this valve completely, to close or open this valve completely. So this is the beauty of your integral term. So for integral term, obviously rise time I can say will again decrease as rise time will be decreased. Why? Because it again converts it into a ramp. So it converts the error signal into a ramp. So obviously there is an error signal, there is an error signal. So it will that due to that effect of error signal, it will this ramp, this slope will increase and it will achieve the required height earlier than the original system. So your rise time obviously will decrease, your overshoots will increase, settling time will also increase, and your steady state error will be 0. Now what about derivative term? Now what about derivative term? Now derivative term actually doesn't have any significant effect on your steady state error, but it can, if I would say in the layman language, it can calm down your response. It can decrease your overshoots because derivative has the property to make slope to a constant line. So whenever it opposes the rate of change. So uh, derivative term can anticipate the steady state error. I would say that it doesn't have any effect on the although it doesn't have any effect on the steady state error, but it can see the rate of change of your system and uh, eventually sets up its parameters or its value so that your system response is more kind of stable. It settles in less time. There are less vibrations. There are less oscillations due to this property. So derivative term, actually I would say that rise time would have a minor change, and main its impact would be on overshoots. Overshoots will be decreased. If you see that integral term is increasing overshoot, but it is decreasing steady state error to zero. So if you combine integral and derivative controllers, so your overshoots will also be in limit and your steady state error will also be zero. So these are always used in combination, so that the bad effect of integral controller over here is being compensated by the good effect of derivative controller over here. So overshoot decrease eventually, obviously, whenever the overshoots are decreased, then system is settled in less time. So settling time is automatically decreased. Integral controller was increasing your settling time. Integral controller was increasing your overshoots. So for these 2 points, you can install a derivative controller to keep overshoot and settling time in control. And if you use I and D controller in combination, your settling time and overshoots will be controlled and your steady state error will also be zero. This derivative term has kind of no effect on your steady state error. For reducing steady state error equal to zero, you use integral controller in combination to this. If you only want a system where you are desired to reduce the overshoots and settling time, and you are not interested in your steady state error, then you can use derivative control alone. But if you want that your overshoots and settling time are improved, but your steady state error must also be equal to zero, so in that scenario you have to use the derivative controller in combination with the integral controller. So if I draw a PID controller, it would be like U of t input, and then I have P, I, and D. For P, I have again Kp of t, Kp E of t, I would like to write, and Ki integration E of t dt, and then Kd d over dt E of t. Add all these responses, then you have a process which, or I can say you have a plant to be taken care of. And then this is, let me draw a feedback path as well, and this is the E of t. So this is actually uh, same as this one. Sorry. So this is same actually as I made the system over here, but I have now expanded this k. I have now expanded this k. So this K is now divided into three parts. One is proportional term, one is integral term, and one is derivative term. So Kp of t is the proportional term with respect to error. This is integral with respect to error, and it's a derivative with error. So this is the block diagram of your system, of your plant with a PID controller. If I try to write it in mathematical form, it would be actually the same. Just trying to write it in an expression, it would be Kp E of t plus Ki integral over t E of or deta, and plus Kd dE of t over dt. So this is the equation for our PID controller uh, in time domain. When I try to write it in S domain, it will be Kp plus Ki over S plus Kd into S. This will be in Laplace domain. This will be the equation of your PID controller in Laplace domain. Just after rearranging, I can have Kd into S square plus As plus B over S is equal to Kd into, obviously the values will change, so I am just writing Z1 plus Z2 divided by S. I have taken a value Kd constant, then obviously Ki would be at this point I would have Ki over Kd, and at this point the constant will be Kp over Kd. So that is why I am writing it Z1 Z2S. So you can take a constant outside and you can have this expression. So it means that your PID controller, the thing to observe is just ignore what I have done with the constant, because let's suppose Kp is a constant, Ki is a constant, and Kd is a constant. I have taken a constant out, and these the constant over here will automatically settle. The point that you have to note or you have to observe is that this becomes a second order system, and there is S in the denominator, and in numerator you have a second order equation. If you have a second order equation in numerator, it means your PID controller has two zeros and one pole at origin. This is important observation. One pole at origin due to this S, and two zeros due to this second order system. Now you can have these values of Kp, Ki and Kd. You can have, whenever you have Kp, Ki and Kd constant, you can set the values of Kp, Ki and Kd, and you eventually can have your poles and zeros at any desired location. Let's take an example. Let's take the uh, example of the effect of these two zeros and one pole on any system. For example, if I have a system 1 over s plus 2 into s plus 3, which means uh, one pole at minus 2 and one pole at minus 3. So if I have this kind of system, then it means that this part, if I would, I try to draw the root locus of the system, it means that there will be a portion of real axis which will be the part of root locus over here. Then these two roots will move towards each other. There will be a breakaway point. One will move up, one will move down. Either they will go in any direction. If they are crossing geomag axis, then one will move on this side and one will move on this side, and your root locus of your system will be like this. But after introducing a PID controller into your system, PID controller has one pole at origin and two zeros. It means your new system will be one pole over here. These two poles will be minus at minus 2 and minus 3. You have two poles, and then you have two random zeros at any location depending upon the values of Kp, Ki, and Kd. So now instead of this portion, you would have this portion of this portion of real axis at as the part of your root locus. This will move to this zero and one will move to this zero. So earlier two poles were going towards infinity, and they were becoming the source of instability of a system. However, by introducing a PID controller, you have given a terminating point to these poles in left half plane. So these poles, instead of going to the infinity in the right half plane, instead of having a tendency to make a system unstable, they now always remain in the left half plane, and system will never become unstable. For this pole, it will go to minus infinity. and the your new root locus will be this. Older root locus without PID controller, the system had the tendency that your two poles are going to infinity via on the path of asymptotes. However, when you added a PID controller, two poles got their zeros and they terminated, their root locus terminated in the left half plane, and instead of going towards infinity they just terminated in the left half plane, and the possibility of system becoming unstable becomes absolutely zero. So this system can never become unstable. However, this system has the possibility to become unstable when your process parameters or your k or your variables move behind a certain threshold value. So this is you can visually see with the help of this example that uh, how a PID controller helps to to enhance the stability of the system with the help of this. So you already we in this portion we discussed how PID controller helps us to improve the system response, and at this point we discuss how a PID controller improves the stability of the system. So I think that's enough for today. Again, uh, in case of any questions, you can write email at rafi.chughtai@uit.edu.pk. This PID controller topic is, I am again closing this lecture with a note that this topic of PID controller is of extremely importance. So you have to give the due intelligence or the due attention to this PID controller topic. You can search web as well if you find anything confusing in this lecture. You can, although I have tried to keep it as simple as possible as uh, you are listening to this controller for the first time, so I have tried to make it as simple as possible. However, still in case of any confusion, you can ask me, or either you can take help from web for the actual responses of your system, such kind of responses. So ji, thank you very much. See you next time in another lecture. Allah Hafiz.